Okay, hello everyone. We are very glad to have opportunity to give the presentation on the Black Hat Europe, and we will share some interesting finding about MPU usage in the real RTOS. And at first, a short introduction for us. And my name is Zhou. I'm the associate professor at Huazhong University and of Science and Technology China. And Zhouqi Jiang is my master student. And this is also a joint work with Dr. Guan. He is associate professor at the UJA. We are all focused on the system security, especially in the IoT area. And this is a great pity for us cannot be in the London due to travel restriction. And I hope everyone will be safe and healthy during the pandemic. Okay, go back to our presentation. This is the agenda. I will first give some basic background about the MPU and its adoption in the popular embedded OS, and then we will focus on their common pitfalls and limitation in their MPU usage. We will also give some mitigation suggestions and these issues, and finally summarize our findings. So what is the MPU? I think everyone here will be familiar with MMU. It has been widely used in our modern operating system for memory protection. However, MMU usually absent in the microcontrollers. As an alternative, ARM, the leading chip designer for many MCUs, has proposed the MPU as a stripped-down version of MMU to protect their system. The function of MPU is simple. The MPU can send different permissions for different memory ranges based on the current privilege level. And if the permission is valid, a fault handler will be raised, and it can only be configured by the privilege code. So how to program the MPU? Typically, only the 3 registers are needed. The control register is used to enable the MPU, and the address register is used to configure the start address and the set of each memory range, and the attribute size register is used to configure the access permissions, including the read, write, and executable for different permissions and memory address. And note that the first one range can be further divided into 8 sub-ranges, and it all have the same permissions. And also, if you enable the background ranges, the unmapped memory space can only be accessed by privilege levels. And also, we can see there are some some constraints for the memory ranges. First, the range at least for the 3 bytes, and the size must be the power of 2 for the line. And the most constraint is it must be the range numbers. It up to the 8 for the ARM Cortex-M series. And in the ARM V8 arch, the programming become a little bit flexible, and the number of the MPU ranges will be increased up to 16. And also it uses separate and start limited address to define the abstract address space for memory range. And it will also introduce a new memory attribute indirect register to share same memory address with different memory ranges with different access permissions. So it seems MPU should be useful, but let's look at how the real-world OS uses MPU and what the specific script function can be provided by the MPU. First, we can see the OS always sends the code range as non-readable to achieve code integrity, and no accessible for the data range for the DEP. Also can be used to achieve the start guard with a small inaccessible memory range after the stack binary. And most importantly, the RTOS can take advantage of MPU to achieve the user space and the kernel space separations. We will detail this later with the concrete examples. And we first see whether these security features are all adopted in the wild. We just review the popular RTOS, their code and documents, but to our surprise, as shown in the tables, only a few OS use MPU, especially for the open source. Even if the MPU is supported and only a few security features we can say are enabled by default. So in this work, we are trying to find why the MPU has been outcast in the RTOS. Okay, I will share down the root cause of these situations. First, we summarize the common pitfalls as as 4 points. First, I will show how to disable and easily pass the protection provided by the MPU with a real-world RTOS. And first, some OS like RLT just use a few MPU features and it runs all the code under the privilege level. So it just provides some basic protections, less DEP and the stack guard. And for the DEP, the RT just able the MPU range number 0 to cover the whole RAM range as a no accessible. And for the stack guard, the IoT defined permission of the last 13.2 binaries of the main stack as read only for the kernel, and also for the each task, it also assign a small inaccessible memory as the binary of the stack to present the task overflow. And note that it cannot detect the task overflow of the individual task form, and it also cannot detect the control flow hijacking attack. So the problem is here. I think, as just mentioned before, the MPU can configured by the privilege code. So the MPU can be disabled by the control flow hijacking attack. And also the IoT also provides the attacker an easy to use driver API for the MPU configurations. Like here, the MPU disable functions in the IoT kernels we found. So any attacks, if have just overflow buffer, it can be taken advantage by the attacker, and then he can to redirect the execution to this MPU disable functions and just to shut down the MPU. And this is a short demo to show our attack process. And see, we just craft a receive handler functions with just a buffer which can be overflowed by the attacker. And then we start the RTOS. And we also can see the disable functions. And just after the RTOS start, we can see at first the MPU is enabled, and then we call the receive function to input our shell code. It will be overflow the buffer to redirect to the MPU disable functions. Now, after we just input our shell code, we can see the MPU able bytes. The last byte in the MPU control register has been changed. Now the MPU has been disabled. Okay, now we go further to see a more completely used in the FreeRTOS MPU. The FreeRTOS MPU uses the 5 range by default, as shown in the table, and to achieve not only the DEP, and it also has been achieved the kernel and the task solutions. And for the CIP and DP is adopt very simple. It just use this memory range for the no readable and no accessible, and to achieve that. And for the task memory solution and the kernel memory solutions, it will assign the kernel code and data range can only by access the privilege code is the kernel. And the task, it can only access its own task stack only, and he cannot to access other task stack and also the OS kernels. So if what will happen if a task wants to use the kernel API? It must use the system call. And for the FreeRTOS MPU versions, it does not provide the kernel API for the system call individually, but just wipe the original kernel with the previous switch functions with the SVC handlers. So for example, it's an unprivileged task wants to use the kernel function. Let's hear the MPU task delay. It will force to call the system call, and system call will force to read the privilege and then call the kernel, and the kernel will go back to the system call and reset the privilege and then go back to the task. So there we can see an easy bug is the unprivileged task it can raise its privilege by just call the internal function like the web functions port receive privilege functions. And it also can be easily patched. And the FreeRTOS patched ways to change the original function as a as a macro, and so it cannot to directly call the functions, but it's really but the problem is really solved. Let's go deeper with these problems, and we can see the patch code is at here. And when the system call called task delay functions, it will force to judge the is a privilege or not, and it's a unprivileged code. It will raise its privilege as a privilege code, and then to go to the kernel functions. And the problem is here, the value used to store the original privilege level is on the stack. So if there's an overflow or the attacker can manipulate the value on the stack, it can just change this privilege level. So when it go back to system call, it will judge again the privilege level or not, and this will be filled. So the privilege will not go down, will not drop the privilege. So it will just return for the original task, and now the task has been a privileged task. So let's go further to detail the explosion steps with a simple buffer overflow. And we can see this is the buffer, and it can be overflowed. And we forced to overflow to just the return address. And so to make the program to jump to the internal SVC interrupter to reach the privilege. And next, it will go to the kernel function. And we further to overflow the privilege levels on the stack. So when it finishes the kernel functions, here, it will to judgment the original privilege level and from the stack values. And the stack value here has been changed with the privilege level. So it will directly to return these functions and will not to reset the privilege. We also recording a short demos. We can hear this is the unprivileged task, and it will to and we just start, and it will call the receive functions, which have a receive buffer which can be overflowed by the UART interpret. And now we can see at first the current stack is unprivileged. Now we just input our shell code to overflow the return address and also the privilege level value. Now we can see we go into the system call as the SVC handle. Sorry. Now we can first say after the interrupt, the privilege have been raised. Now go further here, it will force to to restore the privilege level from the stack, but stack now has been overflowed by us as a privilege level. So it will just to return. It will not reset the privilege, and we just to see the privilege level right here. And now we can see the current task is privilege. And the demo is finished, and we also can output from the UART. And this bug is also further patched by the current FreeRTOS. It just to let the privilege level judgment at the beginning of the with the control register in the system call. However, we found other problem can still works. Is that although we cannot to just manipulate the value on stack to manipulate the privilege levels, but we found the FreeRTOS can create a task with these kernel functions named the task create. And these functions also has been wiped by many system calls. For example, as a MPU task create, MPU task create static, and this problem is since the unprivileged task can also call this create task functions with MPU wrapper, and this task have a parameter and to indicate that the task is the privileged or unprivileged. So the unprivileged task can call this system call to directly to create a privileged task. As we can see, the wiped system call here, this parameter to indicate whether it's a privileged task or unprivileged task will be created. So we assume just an unprivileged task and to can call this system call. And this system call will call the kernel and to create a privileged task. So it can the privileged task can be itself. So we can also achieve to the privileged solution. We also detail the exploitation stamp here with a simple buffer overflow, and further we just to overflow our return address to these web functions here. And further, we can just to overflow any parameter of the new create task, and we can also to rewrite the task A, but with like here, like with the high privilege level, which indicated by these parameters on the stack. Yeah, we can see when I go here, a new stack with the privilege level will be created. We also record a short demo to show this problem. We can here when we start with the unprivileged task, and it is unprivileged right now. And we just to call a function which has also a buffer. A buffer can be overflowed. Now we just input our shell code to overflow the buffer. Yeah, we can here we first to jump into inside the the task create functions here. And now further it will to to set this new task per minute from the stack which has been overflowed and manipulated by us. Now here we create a new task with a priority level with just the same task code. So when we go back to this task, we can see this task has been the privilege right now, and it's just the same task code, but just a new task we just created before. It's a privilege task. Now we will also to discuss some other pitfalls of the MPU, and we further to find if the implementation of the MPU has no vulnerabilities, but the protection provided by MPU is also very limited. For example, it cannot protect the interrupt handlers, since all the interrupter vector address tables cannot be checked by the MPU. And the interrupt handlers is also always being under the privilege levels. So the developer cannot assign specific interrupter for the unprivileged tasks. And also due to the constraints of MPU is not very suitable for protecting the peripheral with a small range. And also the advanced protections as the no execution only or it cannot be provided by the MPU. And the privileged permissions is also always greater than the unprivileged permissions. So it cannot protecting some very sensitive security applications when the OS has been compromised. And also to leverage MPU to realize the solutions is also very will also incur many overhead. For example, in our experiment shows that for the kernel as task solutions, the privilege switch will incur the many time delayed, and also the MPU range also need to be reconfigured during the different tasks. So it will also to incur the time delay. And also the limited MPU range for the real world applications also constrains its usage. We found there are very few user-defined ranges for the peripheral solutions, and as shown in the table before, Node OS provides a peripheral solution by default, and very few also available range for the memory share between two tasks, and we also found Node OS provides shared memory protections by default. And it's also impossible to enable many functions at the same time. As we can see, the Sun Tizen OS, when it enable all the MPU furnitures, it has no available MPU ranges for the developers. And also porting the MPU with the real RTOS will also to incur many complete issues. We have seen many complaints on the developer forum. And last, we will give some mitigation suggestions to better use MPU and to minimize these pitfalls. First, we can we need to be careful about the privilege overlap. We can see the most OS just use a lower number of the MPU range for the kernel protections, but the ARM allows the MPU range to overlap, and the higher numbered range always have the high priority. So we just recommend the OS should use the high number MPU range for the OS protections, and just let the user define the MPU range at the lower numbers. Second, as I just mentioned before, any privilege solution entrance should be careful, especially for the system call. Ideally, we just recommend the OS should use the individual system call for the kernel APIs to force the privilege switch, just like the modern OS. And if not, you need to perform additional checks for the caller to make sure the privilege will be dropped after system call. And also the privilege separations is also needed for the general protection. Although some OS just want to provide some general protections without the user space and the kernel space separations, but we recommend the system should drop the privilege immediately after MPU configurations. And we also give some advice to minimum the range usage, because the number of the range is very limited. For example, we found none of OS take advantage of the subrange, and subrange can have a lot of for us. First, we assume there are two tasks. There task A just want to use the 3 KB for their stack, and the task B will use only 5 KB for the stack. But as we just mentioned before, due to the align problems, we have to assign 8 KB for the task B and 4 KB for task A. The total 5 KB memory will be used. And then if we just enable the sub-range features, there are only 1 KB memory range that we needed, and we can switch them. And if we run task B, we can just enable the higher sub-range and disable the lower sub-range for task A. And if we run task A, we can just enable the task A for the lower sub-range and just disable the higher sub-range. So to take advantage of the sub-range, we can also to save many MPU ranges when we want to achieve the peripheral protections. We assume that there are 8 peripheral. If we only want to assign the peripheral G, E, A as a privilege level, and other is unprivileged level. If with all the sub-range features, we have to assign at least 3 separated MPU ranges. But if we just enable the sub-range functions, there are only 1 MPU ranges is needed. We can just disable the 3 privilege access, and they will go to with the background range, which is just the privilege access, just satisfied our usage, and the others will just go with unprivileged access. So as last, to protecting the user-defined results, we can also learn from the academic communities. For example, some research proposed to install the task with the memory wheel switch, which just reduce the overhead incurred by the privilege switch. And just can run the task and the kernel also all under the unprivileged levels. And also other research tries to install the some small functions and based on the code functionalities, and it will also do not use to many MPU usage. And also the redesign MPU will be better, can address this problem fundamentally, but it will cause a hardware. And also we can use the trust zone. It will provide the trust zone extensions. We can also use the screen range for the additional ranges to assign more MPU ranges in the privilege levels and in the square or the normal world, and also some new hardware architectures that translate provide a new MPU, which are not only validate the data access, but additionally consider the current active execution point as subject to perform the access. And we just summarize our presentations. We found MPU as ready-to-use security features, but it's rarely used in the real-world product. And we just start to find their common pitfalls. And some faults we found is hard to rediment in the short term. We just gave some recommendations for better use of the MPU. At last, we also disclose our funding with the MPU kernel and their developer team. And the RTOS developer team also has now our fundings. But he thinks the benefit of disable access to MPU is limited because it only provides such limited protections, and no, the user space and the kernel space relations has been adopted. And this is all my presentations. And we are all three happy to take any questions.